Now we will see a version of Campbell theorem for marked point processes. For a marked point process with intensity capital lambda A, let f be a function from Rd cross M to R plus. So here M is the mark space, which can be RL if it's a L vector random variable. For a general workspace, I have denoted it as M. This function takes two input. One is first the location and second is the mark itself. And it mapped to a real positive number. Then if you recall Campbell theorem, there we said that expected value of summation of function fxi over all point is given as integration over function x fx into capital lambda dx. Here we have, because it's a mark point process, each point has a coordinate and its mark. The function would be function will it's a function. We have to take the function width of the point and the mark both. So here we are interested in computing expected value of summation of fxi comma mi, and this summation is taken over all points in the point process. So just go to each point, find xi and its mark mi, compute the function, do it for every point and add it. And the question is asked, what is the expected value of it? So to compute that, we will again do the same trick. We will first condition on total number of points, okay, which is n, and condition on that the summation inside will become will have deterministic number of terms. So the summation itself can be outside the expectation. So it is en and then given n, the summation is outside, and then the rest term we have expectation respect to phi, that I can write as expectation respect to xi, and then below term is expectation respect to mi given xi. Okay, so this has two randomness xi and mi. So once I condition on xi, the rest is expectation mi given xi. So I applied conditional probability law three times here. Now, if you look at this expression, where you have to take there is a function x comma m is the mark of x, and then you compute the expectation m given x. So if you look at this, this is a conditional expectation, okay? And once you compute the expectation with respect to m, it will be a function of x actually. So yeah, so x will actually remain. If you change x, the expectation will change, okay? This is a function of x, let's call it f prime x. It can also be written as x because the expectation with respect to mark, so that can also be written as expectation over the mark space of fxm into probability that the mark is in D. Okay, so this is assuming the mark is continuous probability. If mark is take discrete probability, you can just take summation over all range of marks fx comma m into probability that mark takes value m. Okay, so don't get confused. It's just expectation formula. It is a probability multiplied by density and integrated. So if I look at that, I can replace this by f prime x, and this will become just summation of exi of f prime x. Okay. Now this, the mark I have computed this expectation inside, so the remaining term is just a function of xi. So this, if you, I can combine this and n to get expectation with respect to phi. So what I get is expectation with respect to phi of summation of f prime xi. So this is here I can again now apply Campbell theorem because this is just summation of function of xi. So once I apply Campbell theorem, this will be f prime x lambda dx. Okay. So now I will put back the f prime value. It is the expectation of fxm m given x, and then rest is lambda dx. Okay. Now I will also, so this is a valid answer if I know the expectation of this with respect to mark given x, and I can just integrate with respect to lambda dx. Okay. This also means that you compute how many points are there in the set interval dx, and then for that you compute that what is the expected value of the function over the mark distribution, and then you multiply them and add to get the summation value. There's some different forms. You can also write this one. If you remember, this is uh, nothing but some integration of fxm over the probability space of M. So it is fxm into nu x dm integration over the mark space. Okay. Now, if you recall this, nu x and lambda dx is, if you multiply, they will become the Campbell-Mathis measure, which is C dx cross dm. So this will be just integration of fxm on this Campbell-Mathis measure. So you can see that now this looks like exactly Campbell theorem. The mark point process is a point process with this intensity measure. Okay, so if ximi you take that as a coordinate of the point, the equivalent point process, and then this is just summation over all coordinates, and you get this Campbell-Mathis measure. You multiply by the function, and then you integrate it.